So I just want to use this section of the lecture to introduce to you sequences and series. What are sequences? What are series? And we'll talk a little about the sigma notation, in writing sequences and series in a very, concise way and so on. And I think most of you, know what a sequence is. You did anything of that sort in high school? What's a sequence of numbers? Any thoughts?
Sure, a list of numbers linked together.
Okay, that's a start. List the numbers. There has to be some kind of pattern to them, right? Here's a little definition. You rightly say there's some kind of order to the list, right? Not just just random numbers, but there's some order to the list. I mentioned here, each term is called an element. Right? You think of each element as I mentioned here, like the domain, right? You can actually put it in some. We come to what we call a general term for a series and so on, right? There's a little definition there. And these are some examples. And there are types of sequences, right? You have infinite sequences, you have finite sequences, you got what we call oscillating sequences, you got diverging sequences, you got converging sequences, you got converging and oscillating, diverging and oscillating. So remember I said, right? This is just an introduction, right? So here they're telling you that an infinite sequence is basically, one where the domain is a set of natural numbers, and you know that the natural numbers go on and on and on infinitely, right? And here is one. So the sequence is 1, 4, 9, 16. So what you're seeing there, that sequence is made up of, and it goes on and on, right? You said it's going on and on. The input or the domain is a set of natural numbers, 1, 2, 3, 4. And it seems as though each term of the sequence is obtained by squaring the natural numbers. You square 1, you get 1, square 2, you get 4, you get square 3, you get 9, and so on, right? The general term, and notice here how you can write that sequence, right? The nth term, in other words. If you want to know A1, meaning the first term, you put 1 in the place of N1 square, you get 1, that's a general term. There is also something called in some of the textbooks, called a recurrence relation. Recurrence relation, right? Where you might say an plus 1, meaning the next term is an. Well, in this case, what would this be? An. No, it wouldn't be an. It would be n plus 1 all squared. yeah, you might have a hard time coming up with a recurrence relation for this one, but yeah, there's something called a recurrence relation where you relate the next term with the one before that, right? You can come up with one like that. What happened to my? Oh, okay. And here, you're talking about the general term for the sequence, right? We talked about that. And sometimes it's not easy to just watch the thing and tell the general term. You might have to do some playing around, thinking as to, how is it that you get each term of the sequence. This one was easy, but not all of them are very easy. And you'll see in your tutorial, you have some that might trouble you, right? You call for some thinking on your part. And here they're talking about if you have a finite sequence, right? Where you're not having a sequence that goes on and on and on. You want it to end somewhere, right? So like this one, say you're talking about the set of natural numbers up to m, right? Maybe you want 1, 2, 3, 4, and m, maybe it's 10, 1 to 10, and that's it. So look at another example. You want the sequence 2, 4, 6, 8, 10. So the general terms seem to be 2n here, right? But you're saying that n are the values 1 to 5, right? So you don't want it to go on and on and on. Right? You want it to be, I don't know if they put some dots here, but I think they meant it must stop at 5. Yeah, oh, they're saying it here, yes, yes. This is if you go on and on and on, this is an infinite sequence. And the value of n goes on and on. But here, 2, 4, 6, 8, 10, and you stop there, right? So you have a finite set of numbers as contrasted with an infinite set of numbers, right? So this is a little example. You have a sequence and the general term is 2n minus 1. So let's say you want to force 5 terms. You just substitute in the place of n, the domain 1, 2, 3, 4, 5, and you do your arithmetic and you get your 5 terms, right? Very simple. This is another one. It's a finite sequence. They want 4 terms, and you're giving the formula here. And this is a good example of what we call oscillating and converging sequence. You notice that? You go -1, that's -1. Notice the sign, right? Then you go to half, and you go back to -1/4, and you come back to 1/8, and so on, right? If you were to go on, it's actually getting smaller and converging. If this was to go on, let's say you're not considering 4 terms, you're probably considering 100 terms. You'll see that number will come down. It's going to oscillate and then come down to a very small, a number of very small magnitude, right? As you can see here, -1, half. The oscillation comes from the sign, right? Negative, positive, negative, positive. So it will go negative, positive, yeah. Right, and a lot of those you'll see like this -1 to the n power, because when the power is even, you get a positive, and when it's odd, you get a negative, right? Lots of the oscillating sequences will behave that way. Yeah, this is what I was, let's see this one. Find a formula for this sequence. You have these here, right? 2, 3, 4, 5. And you want to find a formula. Well, it seems as though you're taking the natural numbers 1, 2, 3, 4, adding 1 to them. So your formula is just n plus 1. A subscript n is equals to n plus 1. Right? This will be easy to write a recurrence relation for. Like if you were to write a recurrence, I think you had a little tough time earlier. So this one will be a n plus 1 equal to a n plus 1. Meaning the previous term, notice the next term, which is a subscript n plus 1, is equal to an, which is the previous term, plus 1. Right? So this one, it was easy to write what we call a recurrence relation. Yeah. So another example. You have to come up with the general term. So the general term is 3n. These are not hard. So now that we're introduced to sequences, we want to know, well, what's a series? What's a series? Well, a series is just the sum of a sequence, right? It's just a sum. I forgot to mention earlier that when we talk about sequences, you'll see in some textbook they refer to them as progressions, right? And we'll talk a little later about two types of progressions in particular: arithmetic progression and geometric progression. We'll come to that in just a moment. Yeah. So what's a series? A series is simply the sum of a sequence, right? And that's what it is. And we give you some examples here. So you have this sequence 2, 4, 6, 8, 10. Series is simply the sum of all of them. We had that oscillating and converging series sequence. Well, the sum of it, that's a series you see here. All right, so the series is simply the sum of a sequence. That's all. Sometimes to indicate the sum of a sequence, we want a more concise way of writing it, right? So this is how we're going to write the summation of 2, 4, 6, 8, 10. We want to write that in a very concise way. We're going to use what we call the sigma. That's a capital letter from the Greek alphabet, right? We borrow it and we're saying that's a summation notation, right? Yeah. So to write the sum of 2, 4, 6, 8, 10, we're going to say that it's the sum of, notice, we're going to replace the x subscript n, which is the general term for the series, right? Or an, a subscript n. Remember we used that earlier? And notice the author here switched from a subscript n to x subscript n. And this here, look this part. This is how you might write it. So here, this is the general term for the sequence. And you want the sum of all the terms from n equal 1 to n equal 5. Right? So what that means really is this. Because if I put 1 in the place of n there, you get 2. If I put 2 in the place of n here, you get 4. If I put 3, you get 6. If I put 4, you get 8. If you put 5, you get 10. So instead of writing the series like this, we can write it very concisely here using the summation notation. Right? You put the general term inside there and you say, well, what values you want n to take on. If it's an infinite series, you can write, this is what you can write the sum of 2n from, sometimes you don't see n equal 1 here, you might see 1. What you really mean is n equal 1, right? So some textbooks will just put 1 there. To infinity. Yeah, meaning that, well, we're talking about an infinite series, right? And not always do they use n. Sometimes you can see the sum of 2r, where r equal 1 to r equal 10. Some books drop out the r and you just see 1 and 10, no r. And you fill in the big blank that, they mean r must take on values from 1 to 10, right? So this notation, you'll see it in a lot of places. See it a little in calculus, you'll see it in statistics a whole lot, right? So get used to it. So these are some examples, right? So if you have a set of numbers, sequence, and you want to write it using the summation notation, right? Notice a little difference here. They're using x subscript k equal to 1, right up to k equal n. They didn't even write k equal n. Notice, and I just talked about it. They'll drop out that k, and they might put 1 here, and they'll put n on top, meaning that k can take on values from 1 to n. And that means n means whatever n value you want to stop at, right? Whatever value. So if you want a 20, 30, 40, infinity, it's up to you. And this is an example. So you have this series, k squared plus 1, that's a general term. And you want to write it out using the summation notation. You don't want to write out all the terms. So all you do there, you substitute 1 in the place of k, then 2 in the place of k, then 3 in the place of k, right up to 5. And those are the terms there, right? And then you add them up. You add them up, right? And as you will realize now that adding up a lot of these numbers will be a problem. And therefore, we're going to move on to, in just a moment, where they're taking these series now and categorize them into what we call arithmetic series, geometric series, and so on. Another example, this one seemed to be oscillating, right? So you have the sum of -1 to the k power times root k plus 1 from k equal 2 to k equal 4. Right? So all you do is substitute k. Notice it doesn't have to start from 1. K doesn't have to start from 1. It can start from 2. Right? Later on, you can even see that k can be a negative number now. Right? So let's not go that far. You can actually have that. So you have k equal 1, k equal 2, k equal 3, k equal 4, and you have those values when you work them out, right? Of course, you can't really simplify this much further, right? You're following?
Yes, sir.
Yes, sir.
Yes, sir.
No feedback whatsoever, man. People sleeping in this class. Well, these are just something for you to try on your own. All right, you got plenty in your you got plenty in your tutorial worksheet, huh? Good. So we want to move to talking about some particular types of series, right? And two of them we'll talk about is arithmetic progressions and geometric progressions and the associated series that goes with them, right? The sum of the series, the sequence. Good. So we talked about sequences already and what's a series. We want to go to this here, arithmetic sequences and how we can find the sum of them. That's a series now, right? So An arithmetic sequence is one where each successive term you seem to be adding something on, right? So if you were to take a term and subtract the one from before, you have a number. Then you take the next one, subtract the one before, you always have one value, what we call the common difference, right? And you have an example there. That 2, 5, 8, 11, 14. And what you're seeing, if you take 5, subtract 2, you get 3. You take 8, subtract 5, you get 3. Take 11, subtract 8, you get 3. So you have what we call a common difference, right? You have a common difference. And you can actually now write down the general term of an arithmetic sequence if you were to know, like, maybe the first term and the common difference. And so there is a relationship we can use, right? Look here. Right, so this is it. The nth term of an arithmetic sequence is equal to A1, which is the first term, plus n minus 1 times d. Right, and you can see that if I were to, let's take a sequence, right? 2, 4, 6, 8, 10. Let's take this. So the common difference d is 2, d equal 2. So look at this. If you take this, and this is the second term, right? Second term. So that's 2 minus 1, which is 1. So 1 times d, which is 2, plus the 2 will give you 4. Right? Look here, look how we get 6. Right? A3 is equals to 2, which is A1, plus the third term minus 1 times 2. And you get what? 2 by 2 is 4, plus 2 is 6. See that? So the nth term is the first term plus n minus 1 times d. Right? Because the first term is A, the second term is AD, third term is A plus 2D. What am I writing? Wrong. A, the first term, the second term is A plus D, third term is A plus 2D, right? Fourth term is A plus 3D. Do you notice that? It's 1 less, what? First term, no D. Second term, 1D. Third term, 2D. Fourth term, 3D, right? So the number of D's is 1 less. That's where that formula comes from, right? There is an interesting story behind we come to that just now, right? Yeah, we just talked about this here, right? There is an interesting story behind the sum of an arithmetic progression or sequence, right? And the story has to do with this guy here you see on screen. This is just a painting. We didn't have, I don't think they had photographs at the time, so they just had to paint the man. Johann Carl Friedrich Gauss. I think that's how you say it. Johann Carl Friedrich Gauss. I hope I'm pronouncing the man's name correctly. But there is a story, I think it's on the other slide, right? So the teacher gave them, they make him nice in the class, right? He's in primary school and they make him nice in the class. And the teacher said, listen to me, all y'all, y'all are to add up the numbers 1 to 100, right? And within well, they say in seconds here, Gauss produced the answer. And the teacher wanted to know, well, how did he do that, right? And I think they're trying to give you an explanation here. Let me see if I can show you what he did, or what we think he did, right? So he took the numbers 1 plus 2 plus 3 plus 4, right? plus, all right, we go 97 plus 98 plus 99 plus 100. And then you go here 100 plus 99 plus probably 98 plus, you know, and then you come to, okay, let's go with 3 plus 2 plus 1, right? So, oh my, what's this? Yeah. If you were to add here, what if you are seeing at the bottom? You get 101.
Yes, sir. We
Then
can
you have
understand.
101. Then you have 101. Right down to 101 plus 101 plus 101, right? So you basically have 100 times 101, but that's twice the sum. So you take that and divide by 2, and you'll get the answer 50-50. Right? So it's a smart trick the young boy did in primary school, just imagine. And he got the sum of the arithmetic series there, right? He's a rather brilliant guy. They used to, I think some of the writing from that time referred to him as the Prince of Mathematics. He died very young. I think he died young, 31 years or something. Most of these guys, they have issues, you know. I think he died. I can't remember how he died. It was suicide or what. And they said when he died, he burned most of his notebooks, and it took mathematicians about 50 years to verify a lot of his findings. So in other words, he put back mathematics 50 years. Yeah. I don't know. So suicide is a terrible thing among mathematicians. You all probably know we lost a lecturer the other day to suicide. Young boy, extremely brilliant. So sorry. Yeah. And from that little thing I showed you there came this formula, right? The sum of an arithmetic series is n into a, that is first term, plus the nth term over 2, right? So some textbooks have it this way. You see some textbooks write it Sn is equals to n over 2 a plus L, right? Which means it's first term and the last term. Same thing. So once you know the first term, you know the last term, and the number of terms you're dealing with, well, you can just put it in that formula, right? Of course, they have problems that deal with all variations of this. You know, they might give you the number of terms, the last term, you have to find the first term. Lots of things they can do and so, right? You'll see, I think if you read the notes I sent you, you're going to see a lot of examples in them, right? This is an example they are giving you there. So you have a sequence of numbers here, and you want to sum them, right? It says find the sum for 20 terms, right? So you already got n. N is 20. You look at the series, first term is 2, right? Now you don't know the last term, so you put it in the formula, this formula here, A20 equal to 3 times, well, 20 minus 1. What is it? Is there an error here? Let me see. So you want the 20th term, right? So A20. So that'll be 2 plus 19 times D. And what's D? These seem to be 3, right? Will that give you 59? You have it there? Doesn't sound right. Is that correct? 19 by 3 plus 2. 19 by 3. Yeah. 59, right? I'm having trouble knowing what they're trying to do here. Anyway, good, yeah. So 59 being the last term. So you know the first term, you know the last term, and you know the number of terms, right? So you substitute them here, substitute them there, and that's your answer. There is another formula, let me see if it's on the next slide, for the sum of an arithmetic series. Let me see if they have it. No, they don't have it. So there's a formula, I think, going like this. Sn equal to n over 2 bracket 2a plus n minus 1 times d. Right? I think there's a formula like that. And that combines, you don't notice you don't have to find the last term. You just have to know the number of terms, the first term, and the common difference. And that will give you, right? I think that's in the notes. Check it out. The notes I gave you for the class. It's in there. It's in there. And these are some examples that not examples, rather. It's an exercise. Don't worry about it. You want to turn our attention to what we call a geometric sequence, right? A little different from the arithmetic sequence. The arithmetic sequence, you have to just add 1 to the previous term to get the other. Geometric sequence is a little different, where you have to multiply the previous term by some number to give you the next one, right? That's what it is. And here are some examples. Take 3, multiply by 2, you get 6. 6 multiplied by 2, you get 12. 12 multiplied by 2, you get 24, and so on. You are multiplying this time, not adding. Right? Sometimes you multiply not by a whole number, you can multiply by a fraction. As you see in the second case, you are multiplying by negative a half. Right? And that produces an oscillating and converging sequence now, right? In every case, you notice the number you multiply by is the same every time, right? And if you were to divide, let's say, 6 by 3, 12 by 6, 24 by 12, you would get what we call the common ratio. It's a number you multiply by, right? Similarly, you take minus a half, divide by 1. Take a quarter, divide by minus a half. You take minus 1, divide by a quarter, you take 1/6, divide by minus 1, you will get minus a half every time, right? So that is referred to as the common ratio, right? The common ratio. Right, so here they're illustrating that. But if you were to take the next term, A2 divided by A1, you'll get the common ratio. If you take the third term, A3, and divide by the second term, you'll get the common ratio, and so on. From that, you can see this relationship here. Notice, watch here, that R is actually equal to that, right? When you rearrange this, something interesting will come out. Do you see that though? Do you see that here with the numbers? A2 over A1, A3 over A2. It seems to be this. Nobody is responding. Yeah. and you come up with this formula here, because if I'm to go back to here, the first term is A, the second term will be AR, the third term will be AR square, the fourth term is going to be AR cube, and so on, right? You notice it's the first term times R to the n minus 1. So the first term, right? N is 1 here, 1 minus 1 is 0, so there's no R. Second term, 2 minus 1, you'll get 1 R inside, and so on, right? So the nth term of a geometric sequence is going to be, as they say here, AR to the n minus 1. That's it. So a different formula from the arithmetic series. And then this formula, you can actually find the sum of the geometric series using this formula, right? Sn equal to A1, which is the first term, times 1 minus R to the n over 1 minus R. An alternative to this, the same formula can be written this way. You can write it this way, Sn equals to R to the n minus 1 over R minus 1. It's the same thing, right? It's the same thing. And one, I think sometimes they use this when R is like a fraction. They use this one. Sometimes when R is a big number, like 1, 2, 3, 4, and so on, you put it in front. So raise it to the power and then take the 1, right? Doesn't matter. It doesn't matter which one you use. And the derivation of it is in the notes I sent you. It was very similar to how they came up with the arithmetic series formula. It's very similar approach they use to come up with this, right? It's in the notes I sent to you if you're reading them at all, right? So let's see. This is an example they're giving you here. Evaluate this here. Well, this is a oh my, no. Yeah. So let's say you have to evaluate something like this. What you will do, you can do several things. You can put a 3 outside, out of the summation sign, and then evaluate 2 over 3 to the k power from 1 to 10. That's a very long series, right? If it were, let's just write out some of the terms. I want you to help me. So what would be the first term? 3 bracket 2 over 3. That's all? What would be the second one?
4 over 9.
What would it be? 4
over 9.
over 9. What would be the next one? 2, 8 over
27.
27. So what is your comment, or we get, what do we get? You see, we can take this 3 out. So in other words, it's like you can take this 3 outside here, right? So take the 3 outside and let us deal with these numbers in here, right? So go right up to there, right? So we'll have 2 over 3 plus 2 over 3 square plus 2 over 3 cube, right? That's what's happening. So don't worry with this 3 outside here. Leave that. You can multiply at the end. So you have A being 2 over 3. You have, what is R?
Basically 2 over 3.
2 over 3 as well. Good, right? And you're dealing with how many here? 1 to 10 is 10. So n equal 10, right? So you take all these numbers now, you put them in here. So you'll get S10 equal to 2 over 3 brackets, go with 1 minus 2 over 3 to the 10th power, all over 1 minus 2 over 3, right? And it's always going to go in a bracket here. So you'll do some arithmetic. I haven't done it. You do some arithmetic, and when you finish all of this, you have to multiply by this 3 in front here, right? You will finish it in your own time. I didn't work that out. There'll be a lot of fractions you're dealing with, right? And you'll see a whole lot of these in the tutorial as well. Right, so you just factorize out the 3, leave that for last. Treat what's inside there as a geometric series. You add them up using the formula. And when you finish, well, then you multiply by the 3. And that will give you your answer. Right? The others you see here are, these are some application type questions that yeah, you get a couple in the tutorial worksheet that I sent to you, right? And well, here you're talking about if you have an infinite series where the common ratio might very well be less than 1, right? And that's the series there. That's a formula for it. It works out to be the first term over 1 minus r, right? And again, if you have to evaluate this here, you treat this here, you take the 12 out, right? So it's really 12 bracket, and you get what? 2/3 to the, well, they got to the 0 power there, right? So the first term is 1 plus 2/3, then you'll get what? 2/3 square. First term, second term, yeah. And you get 2/3 square, and so on, right? It goes on and on and on and on and on, right? It goes on, it doesn't end. So if you want to find the sum of this, you notice it's going to get very, very small, because you might end up with 2/3, let's say to the 100th power here. This is going to be almost 0, right? So to get the sum of this, you put it in here. What's the first term? 1 over 1 minus this, the common ratio is 2/3. And whatever that works out to be, that's your answer. And then, of course, you got to multiply by 12, right? And you finish. So, especially when the common ratio is less than 1, the number is going to get small to nothing, right? So they take the formula. Let me go back and show you what it is. Sn equal to Rn minus 1 over R minus 1, right? No, let me do it the other way. Let me use the other way around. Let me use this one. Sn equal to A, 1 minus R to the n over 1 minus R, right? So what they're telling you, if R is a number less than 1, a fraction, half, quarter, when you raise that to a very high power, this whole number turns out almost to 0. So you're 1 minus 0, so you're 1. This A by that 1 gives you this A over 1 minus R. You know, that's what we're trying to get to there. So whenever you have a geometric series that is getting smaller, 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 right? And they tell you to sum it to infinity. Well, this is the formula. S is equals to A over 1 minus R. Right? A subscript 1 before start. And we'll get a lot more in the tutorial, don't worry. In the notes, we have a lot of examples for you. Feel free to read them. Of course, you have your online resources and so that you can use as well. Right? So that's a little introduction there to sequences, series, and in particular, we focused on the arithmetic series and the geometric series.